Okay. So, okay, I know you guys are still recovering from yesterday, but we've got both Project 3 and Homework 3 coming up fast in our rearview mirrors. Um, unfortunately, you saw the email from Professor. We did email him about potentially extending it, but um, kind of as expected, he sort of indicated that the deadlines were the deadlines. So, um, but uh, yeah, but again, we'll talk more about the project. I know we already talked about it a little bit before the recording started. We'll talk in depth about that now, and then yeah, homework 3. I'm not going to have office hours, unfortunately, before the project is due, but do feel free to hit up Piazza or email me with any questions on that. And then, of course, homework 3 is due Thursday, so Wednesday night, we'll hack through any sort of last minute questions on that. So yeah, I love this popped up on my feed the other week and I was like, oh, this is brilliant. All right, so this thing we already talked through, and so next week's discussion. Okay, we got 2 updates for that. So as you recall, we're kind of wrapping up the actual material for this course, and I know you guys have other finals, other exams, but one of the things that we had talked about doing was sort of talking a bit more about career. And my impressions of UCLA Career Services are they kind of leave a lot to be desired, to be frank. And when you're looking at just just kind of feels like they throw you out in the wild. And I think at this point you guys know a bit about my bio, but definitely coming from a bit of a non-traditional thing and being on both sides of the table of having to go out for internships and then jobs, and then being on the opposite end where interviewing candidates for job placement as well, and just kind of being able to talk a bit about that process and maybe provide some insights. The other thing I wanted to talk about specifically, and I know I mentioned this previously, was everybody kind of talks about finding a job, and not necessarily spending as much time talking about whether or not that job is the right one for you. And so I do want to talk a bit about that too, because there's a lot that I kind of realized after the fact, and people don't really sort of train us to think about what are the types of environments that we'll thrive in. And so, you end up focusing on things like the prestige of the company, the amount of salary that you're offered, but without necessarily thinking about, is this really something that I could sign up for years? And as a result, I can't tell you the number of friends and classmates who went through the pain of going into the job market, looking for a job, leak code and technical interview, and just going through all of that hassle. And then within a year, being back on the job market because the company they landed at was just a terrible fit for them. And, an ounce of prevention, if you can kind of think through that ahead of time, maybe that can help out. So we'll talk about all that as well. That's the plan for next week. But just kind of acknowledging that you're balancing a lot. So, having said that, next week will also be our unofficial prom. It's going to be our black tie discussion week. So come dressed in your finest. I know it's probably sitting in your closet gathering dust. So, break them out. Tuxes are welcome. Get your hair done, shave ahead of time. We're going to come in our finest. Full disclosure, I'm probably going to do Zoom black tie, which means business. Okay, Savannah's going now. Bye. Which means business from the top and party from the waist down. That's kind of how I rock these Zoom formals. But yeah, whoever wants to go to CSM148 prom together, you gotta get your dates lined up. There will be multiple awards for best dressed. So do come ready to rock and roll. So yeah, that's happening. Let me see. Okay, we're going to dive into the exam now. Before I do, any other questions?
Why is the profile picture rice?
I asked the
At
same thing
Brandon.
in office
Now that the
hours.
exam's over, I
That's
think
true,
we
Brandon.
should have the answers.
So my friends and I one day were just kind of messing around with profile pictures, honestly, and this one stuck because I was really hungry that day. And I happen to be hungry still right now, so I just put it up as a sign.
That's your flashing, that's your bat signal whenever you want food brought to you.
Exactly.
Could somebody DoorDash Brandon some lunch?
I actually made a virtual background when I was doing when I was teaching over the summer for students, and I made an out for lunch background for
Oh,
people when
that's
I was
awesome.
gone.
Oh, that's awesome. I love that.
So like when I was leaving my station in office hours, I would just put this up to let people know.
You could do one of those technical difficulty screens. Please stand by. Technical difficulty. But okay, the mystery of the bowl of rice has been solved. I'm not gonna lie, man. I was losing some sleep over that.
I'm glad you can sleep easy now.
That clearly that's the only reason I was losing sleep. Okay, anything else before we dive in? Okay, let's do this thing. So we're just going to go through the AM exam. I'm not sure if anyone will be watching or attending from the PM class, but spoiler alert: the PM questions were essentially analogous to the AM ones. I know the variables were changed and some of the things were tweaked, so hopefully the level of difficulty remained largely consistent. But yeah, so I figure if we just go through the AM one, that should provide enough context to sort of know how to solve for the PM one as well. Let me do that. Oh, Brendan, your hand is still up. Is you have something, or is it just? Okay, I'm assuming I'm lowering his hand. I have the power. Cool. Okay, so let's see. Question number 1: interpretation of coefficients in or linear regression. So this is kind of similar to the question you saw in the practice exam. Essentially, in this case, it was sort of asking you to interpret coefficients as part of that model. Let me kind of pause here and ask, did anybody have any kind of specific concerns or questions about this?
I guess the answer. I mean,
Yeah.
not really.
Okay, so again, you have we're sort of trying to model the height of a particular plant, which is obviously so we're looking at kind of a regressionary analysis. So and then so again, when we're looking at the model, we're going to say, okay, well, we're creating a model for the height of a shrub, so that's not a categorical, it's not a classification exercise, it's going to be a regression. And then we're looking at the amount of bacteria in the soil and whether or not it's partial to sun. And then it measures that bacteria is measured in 1,000 per mil of soil. So like 1,000 is 1,000 bacteria per mil. And then we know that our X2 is a categorical, where it's a 0 if partial, 1 if complete. So then it says, what will the height difference? So the first question is, what will the height difference on average between shrubs with a 5,500 bacteria count and a 4,000 bacteria count, assuming the sun is the same for both. So we know our regression model is going to look something like this. We have our beta naught, our coefficient in terms of soil count, and then our term in terms of sun. Now, because we're saying assuming sun is the same for both, we can essentially ignore B2X2 as a term. It's obviously not relevant. And so the only thing that's going to impact the relative difference in height between plants with 5,500 and 4,000 will be this beta 1x1. And because we know that there's a translation of 1,000 translates to 1, so we know that the difference in height will be 1.5, which is obviously the difference between 4,000 and 5,500 times whatever our beta 1 coefficient is. So that's my first, so that's the first part. And then for the second part, So you're saying like, okay, after we have sort of begun to train the model, so we're learning the following set of coefficients. And then it's talking about, explain the effect of the plant being a sun versus partial shade will have on average height. So here we're sort of asking the inverse of that. So let's see here. So we have, if we are looking at, so essentially just kind of zeroing out our X1, because again, now we're just looking at sun exposure. So it's our X0 times 8. And because it's a 0 or 1, it's going to be just 8. So the average difference between will be 8 centimeters between plants with sun versus plants in the shade. So, I think this is the kind of problem where one of those word problems where there's a lot of, I guess, text to parse out, but the actual question itself is, I think, relatively straightforward. But again, it's tricky in terms of just parsing out what's being asked and how to interpret it. So let me pause there, see if there are any questions.
I mean, for this question, the solution is saying just what is the average height, but the question is asking what is the average height, but the solution is saying the difference, right? Like that's not what it was asking.
So sorry, it's saying what is the effect the plant being in the sun versus partial shade will have on the average height of the shrub. So you're not asking what the actual average height is, you're explaining the effect of this variable will have on sort of plant height. Does that make sense? So, I mean, and that's really what that coefficient is saying. It's like, okay, well, all else being equal, what will the effect that this particular feature have on the average height if we normalize for X1 term? I'm feeling you're not loving that, but
I guess they're like the same thing, kind of.
Mm-hmm. Yeah. Well, again, if you sort of read the question differently or you sort of worked out a little differently, again, just submit that and for a regrade and just sort of talk through, I guess, how you interpreted that, and I think we can kind of factor that in to a grading decision. So, all right. Any other questions on problem 1? Okay, decision boundaries. So again, very kind of similar to what we saw in the practice exam. However, now we've got this funky, where is this graph here? It looks similar, but we have this kind of weird sort of relative coloration thing. As I saw some people in the chat mentioned, what we're looking here is sort of relative degrees of confidence. So if you think about your decision boundary and then your sort of decision thresholds, you can kind of think about this as degrees of confidence associated with it. So, obviously your decision will probably sort of align somewhere along here, but, a point that falls along here will have a very high probability threshold of a red classification. Something down here will have a very high probability threshold. Something over here will sort of be borderline. So another way of thinking about this is, yes, we're seeing kind of decision points here, but we're also seeing associated confidence intervals with those decision points, boundaries. But I don't necessarily think that that's sort of as, I guess, relevant for making the decision, but I can see how that would have been confusing in terms of like what we're seeing, like what is this heat map component here and what are we looking at with this? So I guess kind of running through our various sort of things here. One of the things that we had talked about when we reviewed it was just kind of trying to sort of process of elimination these, where you're not necessarily obviously fully confident in terms of what's what, but oftentimes we can kind of get a sense in just trying to work these out. So the first things to know is that we had a KNN with a K of 1 and a K of 5. So we know that when we're looking at that, we're going to see a decision boundary that's largely the same, but as K increases, we'll tend to see it smooth out. It won't be quite as jaggedy as the other one. And so, intuitively, these sort of might be the approach. Like we know in general, K and N decision boundaries can look very, I guess, balkanized. But as we sort of add more K, it'll tend to sort of smoothen out. It'll tend to sort of get a flatter decision curve. So we can kind of sort of work through that. We only really have one sort of absolute linear thing, which is the linear SVM. So process of elimination, it was going to be something like that. D is sort of a little bit ambiguous of which one we're going to go, but we know that sort of an SVM with a nonlinear kernel, when it's sort of projected back down onto that lower dimensional space, we get that kind of crazy nonlinear Swiss cheese looking decision boundaries. So, that would have been, I guess, kind of an educated guess for that one. Then we have both a decision tree and an AdaBoost model. And, similar to what we saw in the practice exam, decision trees will sort of be smooth vertical decisions along the axes of the decision point. Whereas if we're looking at sort of aggregating and incorporating multiple models, rather than it sort of looking smooth, it begins to look very jagged and very rough. And here, precisely because we're incorporating multiple models, we have varying degrees of confidence intervals associated with that. So just kind of working on that, you might say, well, these are obviously connected. This would be a single decision tree. This is obviously incorporating multiple models. Probably the hardest was F, just because it's the least ambiguous here. But, I guess kind of one thing to note here is the fact that we're only dealing with one hidden layer says it's not going to be a particularly complex decision boundary. We might see some degree of variation, but ultimately we're not going to see a particularly sort of complex one. Where you get the really, really complex neural nets is when we get those multiple hidden layers. So we know we're going to look at something a little bit smooth. And then again, by process of elimination, that would sort of be the most obvious choice for that one as well. So, okay, let me pause there, see if there are any questions related to that.
I have a question.
Mhm.
It just like for F, I've seen so many like documentation pictures, or like I think even in the notes where you like for an example of like the RBF kernel, I think it's the sklearn like documentation. They literally use like that picture where there's like a little slight curve or something to say like this is an RBF kernel. So I don't like, I went with that because of like that reasoning. I think for project 2, with like when we had to use it, I just looked it up and they literally gave a picture like that. So I don't know if that's like, if we could like argue that reasoning, or
I think you can definitely argue that reasoning. If you had seen that or something similar in source material, then yes, I think you would be very ground. Because again, this is ultimately this isn't a this is a qualitative exercise, right? So and there are times that you can make arguments. Like there are ones that are very obviously wrong. And, a decision tree will always kind of have these nice right angle geometric decision boundaries on there. So you can very obviously say that like this one is a decision tree, whereas this one very obviously is not. But I think there are ones that are ambiguous. And I think this one in particular is probably the most ambiguous. And so you wouldn't necessarily be wrong for saying that this could be a nonlinear SVM as well, because you're right to say, yes, sometimes it produces these crazy things, but there are times when it also produces something that's just slightly warped.
Awesome. Okay, thank you.
Yeah. So I think that's a very fair argument.
So just to clarify, between part A and part B here, the reason part B is KNN is equal to 5 is because we have that sort of soft boundary between red and blue classifications.
So the reason, so the reason it's not necessarily about the soft boundaries case. Well, you can incorporate some degree of soft boundaries with KNNs. Like you can do relative weighting of weights. So like you could do a K of 5, but you could weigh your the first 2 nearest neighbors maybe twice as high as the residual 3. So there are things that you can do with a KNN. What we're really looking at here more is about confidence intervals. And so it's the idea again that something like here is with a very, very high confidence going to be red, but something along here, yes, our K decision threshold is going to kind of assign something there because of just the 5 points there. But if you're looking at that from a decision threshold, from a confidence perspective, we're a lot less confident about values along sort of this region of the decision boundary versus this area here.
Is that what the colors mean? Because like I had no clue what they meant.
Yeah, I know. Yeah, unfortunately, the colors I know were kind of a bit of a curveball because you guys hadn't seen something like that before. But yeah, it speaks to the relative confidence of sort of assigning a weight there. So the idea being that, where you do your decision threshold may impact that a bit more. Yeah.
Yeah, I wasn't quite sure how to interpret the shade, so when I saw that B had a much tighter boundary, only looking at the red and blue portions that are solid, I thought that would be KNN is equal to 1. Like, that was my idea at first.
Yeah. I think not having that context, that's not an unreasonable explanation for that. So, yeah, again, throw that in the, depending on how that comes out, throw that in there. I think with this one, let me put it this way. I think for this one, as long as there was a reasonable explanation for the assignment that you made, I think you'd be, within your rights to argue for that. Because again, this is fundamentally a qualitative exercise. So, I mean, unless, again, there are a few examples that are very obviously wrong, but for the most part, I think this is to some degree open to interpretation.
Yes, I just wanted to go back to, could we go back to 2? I just wanted to say that I didn't answer that in that format. What I did was I took the model numbers and I assigned them a letter.
I think that'll work. Yeah, that should be fine.
Okay.
Yeah, I mean, the grader shouldn't get tripped up by that.
All right. One time I put never mind. Go on.
Okay. All right. So anything else on problem 2?
Yeah, I was curious with KNN, how do you compute like the what does the shading mean for KNN since it just picks the K nearest points? So I'm not sure how how you get confidence out of that. And also kind of sub question, A and B are both KNNs, so I'm wondering why one of them has confidence shading while the other one doesn't.
Yeah, so Rohit, great question. So the confidence that you would get from a KNN, if you think about it, is the percentage of the vote, right? Because KNN is a first past the post thing. So in a K of 5, it will assign if something is 3, it'll assign if something is, if it has 3 nearest neighbors, 4 nearest neighbors, or 5 nearest neighbors. And so in this case, the confidence comes here. Any point along this axis, the 5 nearest neighbors will be, will be red. Here it'll be 4. Here it'll be 3. So i.e. the majority will still be red. You'll still make that assignment, but we're clearly a lot less confident about something that's getting only 60% of the vote versus something that's getting 100% of the vote. Whereas
that makes sorry, go ahead.
For this one, because it's a K of 1, you're literally just looking at the nearest neighbor. And that's why you have, there's sort of no, there's no, I guess, gradient there because it's whatever just happens to be the nearest neighbor.
Okay, that makes sense. And also in B, there's some regions that are white. So if K is an odd number, I'm not sure how this is possible, but does that mean it should be a tie?
So there it wouldn't be, I think the way to interpret that would be majority are blue, but that's like a really light blue. I agree that the shading there is ambiguous, but like you would say, this is maybe K equal like 3 blue nearest neighbors. This sort of slightly darker blue is going to be 4 nearest neighbors, and then the darkest blue is going to be 5 nearest neighbors.
Okay, thanks.
But yeah, I agree that that's like pretty much just white, so that's not really helpful. Yeah. Okay. A reminder, guys, please make sure to mute yourselves. If you are not, I have at least one unmuted thing, and I can't mute it on my end. Okay, cool. Got it. All right, so then on to question 3. And I'm not going to lie, this was the question when I saw it, I was like, oh no, we have done nothing to prepare you for this. So, I sort of desperately tried to nod, wink to this in office hours, but I know that's really not helpful to those who weren't able to attend that. So probably if you saw this and you hadn't attended office hours, that would have thrown you for a bit of a loop. But generally speaking, as we had sort of mentioned, so for each if an eigenvector says the directionality of the vector, the eigenvalue speaks to the magnitude associated with that vector. So it's sort of how, if this is your direction, the eigenvalue is that coefficient that you multiply to that sort of stretches it to that relative degree. And we were saying like that's an indication of the amount of variance captured along that particular axis. And so one of the things that we had said was like, if you're looking to sort of take a quick and dirty heuristic about how many principal components you want to include, an easy way to do that is just look at the total. If you think about the eigenvalue as being a stand-in for the amount of variance, then you can just kind of look at the proportion of sort of one or more eigenvalues in terms of the total sum of eigenvalues. And so in this case, you would literally look at this as like, so if you just want to look at the proportion of variance explained by just the first principal component, you would take 128 and then you would divide it by the sum of that, which would be roughly 190, ballparking it. So the first question asks, if you want to capture over 90% of the variation, how would you do that? So sort of just building off that, if we know that we're roughly looking at a total value of about 190, clearly this won't be sufficient, but if we just add these two together, we're capturing well over 90%. So that was how we would look at that. Then number two, so this got into sort of interpreting each of the associated principal components. And you know how we had mentioned that if you look at sort of the covariant matrix of each of these eigenvectors, we can kind of look at them in terms of their relative inputs. And so the way to kind of interpret this is we have three factors that were measured: length, width, and thickness. And so if we look at U1 as being sort of the associated eigenvector, we can look at this as being equivalent to the length measure, this being equivalent to width, and this being equivalent to thickness. And this basically says sort of the magnitude that each of those features factors into this principal component, and the directionality of it as well. So, for the second principal component, there's a negative relationship between thickness and this principal component, whereas the other two have positive relationships. And so you can kind of look at both the magnitude and the directionality as sort of how that feature impacts the associated principal component. But yeah, that's just kind of a lot. And I know that was just really sort of briefly spoken to. So I imagine if that was the first time you were seeing that, that would have been very confusing. But so they were saying, if you want to understand the most important factor in figuring the petal's overall size, which factor would you say is most important and why? And so the first thing that you would say is, well, obviously I'm going to take the first principal component, which clearly is the most important factor, and is some sort of representation of petal size. And within that, I can see that length, width, and thickness are all positively correlated with it. But of those, thickness is clearly the most important in terms of its impact. So that's how you would kind of answer that. You would say, well, this first principal component is the most important one. And then within that, we can see that thickness most closely correlates and sort of has the greatest impact in terms of that one. Then it's saying, okay, looking at this second principal component, what kind of flower petals are represented by this? And so again, here you're just kind of looking at the relationship between these. So we have length and width here, which are positively represented, but we have thickness, which is negatively represented. So we're probably going to look at petals that are either, very long, wide, and thin, or counteracting that, things that are very short, thick, short, and narrow. So in other words, you can look at this the opposite way. Like these are either, because these are inversely related, so these are either going to be long, wide, and very thin, or short, sort of small dimension, but very thick, because these are inversely related. So, okay, let me stop there. Let me see any kind of questions, anything to tease out in terms of that question.
Just was curious for part C, like, do you think they're fine if, like, basically I did the matrix multiplication or whatever, the linear algebra, and I said like, oh, it's like 0.22 times this component plus, you know, because they're all factors of each component. Like, does that matter? Because they said what kind of flower petal is this component representing? Answer in terms of our factors. So I basically, that's why I did it like that.
So I don't know how the graders would interpret that, but again, submit that for a regrade in case they
because like the math I did is correct. Like that's what, yeah.
Yeah, and unfortunately, I think we should have specified, like, we were really just looking for a qualitative analysis there, and we really didn't want to get into the math. So I'm unfortunately, that probably chewed up a lot of time.
Okay, thanks.
Yeah, absolutely. Okay, on to metrics. So we have our confusion table here. We have, so remember the first thing to kind of be on the lookout is that how you interpret this table, where y equals 1 is sort of a positive prediction, y equals 0 is a negative prediction. So kind of just making sure that the table's oriented that way. So like this is your true positives, this is your true negatives, these are your false negatives, and these because they are supposed to be positive but you haven't guessed them, and these are your false positives because you did guess them and you weren't supposed to. So in terms of just reading that table, any questions on that? All right, cool. So then where is, hang on, I need to go here. Okay. So then accuracy, precision, recall, and F1 score. So, you know, just kind of running through that. Again, accuracy is the total number you get right divided by the total number. Precision is the total number of guesses you take, or the total number of guesses you get right divided by the total number of guesses you take. Recall is the total number of positive numbers that you sort of get divided by the total number that you should have gotten. And the F1 score just being the harmonic mean of your precision and recall. So any questions on how any of those are calculated, or are we feeling okay about that?
For F1 score, is it okay if we left like our equation in terms of fractions and everything?
Yep. And in fact, here we were explicit in saying it's okay to leave the solution fractional. So yes, that's.
Oh, sorry. Yeah, I meant like fully unsolved.
Oh yeah. That's fine. We did not expect you to work through that. Like, in fact, it would be fine if you just said, if you just plugged in 2 times P times R divided by P plus R and then just reference those. So yes, you would have been fine doing that. So just analyzing the performance, it kind of flows from these metrics here. Clearly, you know, overall accuracy, decent, but where we see we're getting really hit is with recall. Precision's great, recall is bad, and as a result, our F1 score is just not great. So based on that interpretation, you know, how might you sort of improve the model's performance? Well, generally speaking, if our precision is good but our recall is bad, that says that we're being very cautious in terms of the you know, the guesses we take, which means we're probably setting a very high decision threshold. So probably the easiest thing to do is just lower the decision threshold to sort of allow us to make more guesses and allow us to kind of improve our recall score. But then, of course, as we do that, we're going to also get more false positives, so that's going to impact precision. And so just kind of finding the balance between those. So let me pause there and see any questions specifically on 4.1.
I think someone asked you to scroll up to the matrix again.
Oh, okay, sure. Thank you for catching that. Hang on, let me pull up my chat as well because I haven't. Okay, so everyone good on that one? Okay, cool. Then over to the ROC curve, which unfortunately I think was probably a product of not working through an example with you guys, but at least from what I'm hearing with the chatter, there was probably a lot more work done than needed to be done with this. So let's, obviously let's talk about a bit more about what you're seeing with this table. So remember, an ROC curve is sort of looking at the ratio of false positives to false negatives as you lower your decision threshold boundary. And so what we're looking at with this first column is the probability of a positive label. So this row here says there's our model is assigning a 90% probability that the actual label is 1. Whereas this row is saying this data point assigned an 83% probability that a point is 1, but its actual label is 0. So, and what we would be looking at here is that this is a true positive, this is a false positive. So any questions in terms of how we would interpret this table?
I mean, I didn't know the threshold thing, so I took the best that I could do was I assumed the probability was the threshold that was used.
That, and in fact, that's probably the best thing to do. So we'll go through exactly how to generate the table, but that's a perfectly valid approach. So, and I'll talk through why that works in a moment, because as we'll see, it doesn't actually matter how many thresholds. You could have thresholds like 100 thresholds. It wouldn't necessarily matter in terms of the resulting graph shape. Okay, so if you guys are all clear on this table, let's look at what it actually looks like when we graph this. Because if you remember where is the, okay. If you remember, what we're graphing, our 2 dimensions here are our true positives and our false positives. And there's that sort of third dimension, which is the various thresholds that may impact it. But the key kind of thing for generating these graphs is what you're really looking at is the relationship between these two as your thresholds decrease. And so the really, really important thing is like the rate at which you're graphing, the rate at which you're adding a true positives versus adding true negatives. And so the easiest way to think about this, going back here, is you're essentially going to graph this progression. Because just to give an example, it wouldn't matter if you plotted 99, 98, 97, 96. You wouldn't actually add anything until you do this. And then once you add this label, you're not going to shift it until you've added another label. So another label here. And so it's really like as you're lowering that threshold, sort of how are you sort of admitting your various things. Okay, so where is the actual thing? So we start with a true positive. So our true positive rate goes to 1 here. We have a total of 4 each. We have 4 true positives and we have 4 false positives in our data set. So our first one's going to be true positive. Then we have 2, as we go down our decision threshold, we have 2 successive negative rates. So it goes 1 and 2. So at some unseen decision threshold point, we have admitted 2 false positives for that 1 true positive. We then have our next 2 are true positives. So as we continue to go down the decision thresholds, we're going to admit first 1 and then another one. And then after that, we then have a sequence of then 2 false positives. As those thresholds continue to go down, our false positive goes up, our false positive goes up. And then finally, and at this point, when we reach the end of our x-axis, we have admitted all of our false positives. We then have that last residual true positive, but which has no impact on the overall area of the curve because we've already sort of maxed out that thing. So, so again, going back to here, really it's just the ratio of these over time. So it'd be true, false, false, true, true, false, false, true, true, false, false, true.
Yeah, I mean, I'm sure you can see the chat, but like if we had been shown how to do that or like explain that, like
Yeah.
question is more than fair, totally fine. But I think the vast majority of the class was completely lost on this. So
Yeah. Yeah, I think that's okay. That's unfortunate because yeah, I think maybe we should have worked through an explicit example of that, I think.
Yeah, I think all the questions we've done so far, after you explain it, they make sense. And even like I know after someone explains it, it's obviously going to be easier, but I agree with Daniel that if he had just seen even one example, even the simplest example of it, it would have been so easy. Like this is the simplest thing. You just, just drawing lines, it's not, there's nothing hard about this, but just not seeing it makes it impossible.
Yeah.
Yeah.
Mm-hmm.
Why is the X and Y axis like 1 through 4? Because aren't rates like decimals? Or,
Okay,
like,
good.
0 and 1?
Yeah, so okay, great question. So I'll get back to it in a second. But remember, what we're looking at here is, okay, so you're right to say that, you're technically right to say that it should have been like 0.25, 0.5, 0.75, and 1. So you're right, because it is the ratio, technically you're looking at it that way. It was a little bit easier just to write down in terms of the actual numbers that are admitted, but you are technically correct because this is obviously a 1 by 1 square. So it corresponds to a 0.25, 0.5, 0.75, and 1. So yeah, thank you for catching that. I guess it was just easier when you're drawing it out. Just say, okay, there's 8 points here, 4 points each for positive and negative. So I'm just going to kind of plot it out in terms of those. But yeah, you're technically correct that should have been a proportionate ratio.
Yeah, I think that made it more confusing too, because like my graph was definitely, I went from 0 to 1 for both axes.
Yeah. So okay. I feel like I should have just shown you guys an example of that. That would have made it so much easier. But yeah, it's because essentially when you're looking at this graph, you're saying like, at some unseen decision threshold, you will have admitted 25% of your true positives, but you'll have admitted 50% of your false positives. And then there's some unseen threshold here where it's 50-50, some threshold here where it's 75-50, then some threshold here where it's 75 to 100, and then finally 100 to 100. So yeah, so to your question, if you use ratios, I mean, ultimately full credit would be if you generate a graph that looks roughly like this. The axes don't have to be in terms of 1 to 4. Again, that was just an easier way for me to do this. But yeah, I'm hearing you. Unfortunately, I think that was one of those questions where had we given you all a little bit more guidance, we would have you would have rolled through that like a knife through hot butter, as they say. So then calculating the area under the curve, again, it's just, in terms of the proportion. So this is out of 16, this is 2, this sort of area here is 6, so it's 8 out of 16, so it's a 0.5. But any question on how the AUC is calculated?
Wait, sorry, one more thing. You might have said this already, but how did we know that the threshold was 0.5 for like probability?
Sure. So we don't, well, so to clarify, the AUC is 0.5, not the decision threshold. I don't know if that answers the question.
Like when you're deciding whether to admit like another false positive or false negative, like you label it by 0 and 1 from like if it's less than 0.5 and greater than 0.5.
Yeah. Okay. Yeah. Good question. Okay. So again, when ROC curve it doesn't necessarily tell you explicitly what the decision threshold is, but what it does tell you is if you do a decision threshold at a certain value, theoretically, like what would be the proportion of, true positives versus true negatives. And again, because you're really looking at a 3-dimensional thing where the third dimension is your actual decision threshold. But this is just looking at, as the decision threshold is dropped, what is the ratio by which you are admitting true positives versus false positives. So in other words, we're really like, okay, this is, looking at these, right? We have our associated probabilities of a true label versus the actual label. So this is true positive, this is false positive, true positive, false positive. And so there's some unseen decision threshold. That's your z-axis that says if my decision threshold is 80%, I will have admitted, admitted one true positive, but I also have admitted one false positive. If it's 69%, I'll have admitted one true positive, but I'll have admitted two false positives. So it's just, there's that unseen z-axis that we're not sort of explicitly showing in our ROC curve, that just says, like, as your decision threshold drops, what's the ratio of true positives to true negative or false positives that are admitted. So Chelsea, does that sort of, I guess, address that?
Yeah.
Okay, cool. All right. So then the final question here was, what does the score indicate about your model? So you may have remembered this from when we learned it, or from office hours, but one of the things that we said was, like, once an AUC drops down to 0.5, it's 50%. It basically means you are adding true positives with the same, at the same rate that you're adding false positives. So in other words, your model is no better than statistical chance. If you just randomly assigned positive values to your data, you would also get a 0.5. So this model clearly is not really doing any effective work at classifying your data, and clearly should not be used. So, okay. Hang on just a second.